Hello, thank you for joining us today for our webinar on the value of single source providers of emerging contaminant removal, including per and polyfluoroalkyl substances. Here are some tips to enhance your webinar experience. We recommend that you close email, instant messengers, and any other programs not currently in use, as they may interfere with a smooth reception of the webinar, causing slide buffering and poor sound quality. Technical assistance can be found at the GoToWebinar technical support page at the link listed in your handouts and on the slide shown. As soon as you close the GoToWebinar screen, to leave a webinar, a window will open with a survey questionnaire. We ask that you all take a few minutes to answer the survey questions. Your feedback is important to us and helps us improve webinar programming. Before we hear from our speakers, I need to inform you that the mention of specific products or services in this webinar does not represent AWWA endorsement. AWWA does not endorse or approve products or services. I am pleased to introduce our distinguished panel of experts for today's program. Jeff Palisha and John Lombardo from Evoqua Water Technologies. Jeff Palisha is currently the Senior Business Development Manager for Emerging Contaminants at Evoqua. Prior to joining Evoqua, he has held several senior leadership positions with SGS, Pace Analytical, and Vista. Mr. Palisha has specific expertise in emerging contaminants, developing analytical programs, and customer support to meet the needs of this ever-changing market. John Lombardo is a product manager for the ProAct Environmental Services Division of Evoqua. His responsibilities include sales and marketing support, lifecycle management, and product innovation for activated carbon and media products and services. He also supports PFAS opportunities for municipal drinking water and short-term/temporary industrial and military clients. He has been with Evoqua for 26 plus years. And with that, I'm going to hand it over to Jeff. Take it away, Jeff.
Thanks, Billy. Appreciate the introductions. Good afternoon, everybody. As Billy mentioned, my name is Jeff Palisha, and thank you for joining us today for our webinar. Many of you know PFAS are a problem in our community, and maybe that's why you've joined us today. We are excited to put on this webinar today to help you further understand water treatment for PFAS. Here's an outline of what we plan to cover today. I will cover the beginning overview today and then end with a wrap-up at the end. And John will cover solutions and present some case studies. We'll save time at the end of the webinar to take any questions. So a bit about Evoqua. Evoqua Water Technologies is a leading provider of water and wastewater treatment solutions, offering a broad portfolio of products, services, and expertise to support industrial, municipal, and recreational customers. We offer emergency, mobile, and permanent water treatment solutions, and within these sectors, employs one of the largest and most diverse mobile fleets in the country. As we know, water plays an instrumental role in so many aspects of daily life beyond drinking water. So Evoqua provides solutions for customers that have critical water needs across the key market sectors that are listed here. For instance, energy generation, wastewater, food and beverage safety, production and manufacturing, and many more. In fact, today we have 160 locations and over 200,000 installations worldwide. So what's the current status of environmental compliance regulation? So much has been in the news recently, and I'll get to that right after this slide. So for water, currently EPA is being pressured to finalize regulation and evaluate lifetime health advisories through their PFAS action plan. But in the absence of EPA regulations, local states have taken the lead on setting their own state-by-state action levels. And in some cases, you'll see they're more stringent than the current federal interim guidelines. And it's all over the map. It's kind of the Wild West out there. For air and waste, there are potential indications for regulations for PFAS as a hazardous substance. In the EPA current interim guidelines that came out in 2020, they're using the drinking water lifetime health advisory for both PFOA and PFOS at 70 parts per trillion. Along with that, there's limited data of known and detectable PFAS precursors within influent wastewater, as well as the need for improved analytical testing methods that could even detect these compounds. We will expect some updates later this year and early into 2022 by EPA. And one of the things I wanted to mention is, if you saw the news recently with the Biden administration, on October 18th, the EPA announced its PFAS Strategic Roadmap. It's really the EPA's commitment to action from 2021 to 2024. And it provides the agency a plan for regulating PFAS over the next 3 years. This roadmap is the product of the EPA's Council on PFAS and includes a comprehensive program combined with expected timetables. I just thought I'd hit a couple highlights for everybody. And if you weren't aware of it and you want to be aware of it, the full report is available at www.epa.gov/PFAS. So quickly, a couple of the actions: establish a national primary drinking water regulation for PFOA and PFOS, and proposed rule is 2022 with a final rule of 2023. They hope to propose to designate certain PFAS as circular hazardous substances, most likely proposed in spring of 2022, final rule summer of 2023. And the list goes on. So take a look at that website again. It's www.epa.gov/PFAS to find out the latest in the progress that EPA is making on that. So how does PFAS enter the environment and how do we get exposed to it? Contaminants enter the environment through various sources and eventually make their way into the soils, the groundwater, drinking water, and eventually humans. This picture really tells a story. I mean, it all starts with a source. Some examples might be chemical manufacturers or producers, commercial applications, a landfill, your wastewater influent from a treatment plant, and then even firefighting training areas or firefighting foam application that has been applied. All these can contribute through exposure. All these can contribute through exposure routes like occupational exposure, drinking water, atmospheric transport, and contaminated food products, which over time can contribute to adverse health effects. One of the largest studies conducted for PFAS was a C8 health study back in 2005 and ended in 2006. The study looked at human blood serum was performed on a population of almost 70,000 people who were affected by contaminated drinking water with PFOA or C8. The study focused on 6 water districts across 2 states. And with that, I'll pass it over to John. We'll start getting into solutions and the case studies.
Thank you, Jeff. This is John Lombardo. Thank you for your attention today. I'll be covering solutions and case studies. So, a little click happy, my apologies. So for PFAS removal solutions, there's really 2 methods that are currently the most prolific in the business: is adsorption, AD, and separation. So adsorption is an attraction process or an exchange process with adsorption. And basically we call it a capture technology. So it's basically something that captures the PFAS and holds onto it and removes it from the stream. And then separation is exactly what it says. It actually separates it. In this case, it's a membrane. So the 3 most popular treatment solutions currently in the market, at least for municipal drinking water and some of the others, are granular activated carbon, which has been named the best available technology by EPA for organic contaminant removal. It does have other adsorbent properties for other organics as well. And it's a pretty tried and true technology that's been around for a long time. It requires minimal maintenance and it's very effective. The next is single pass ion exchange. It has a lower empty bed contact time than granular activated carbon, so it can usually go at a higher flow rate. Therefore, it takes up a smaller footprint because you can get away with smaller vessels. It does not have a chemical or liquid waste from it. The spent resin can be incinerated, and it again has minimal maintenance requirements. The last is membrane, so RO or NF. They're very effective. They remove dissolved solids, but you do have to deal with a concentrated waste stream, somewhere in the range of, I'll say 10 to maybe 25% of the influent stream. But it is effective at separating the PFAS as well as the other contaminants from your influent stream. So how does granular activated carbon, or why does it work? So granular activated carbon, or GAC, is a highly porous media that has a tremendous surface area that is used for contaminant adsorption, AD. All carbon is not created equal. It all depends on the feedstock. It all depends on how it's activated or if there's any special treatment. The performance really is determined by the porosity and the surface chemistry, which once again is a function of the base material as well as the activation and treatment process. In Evoqua's case, we do a pretty thorough job of matching the application or the user with the best performing carbon for their specific application. So over on the right, you can see a diagram there that shows different pores within the carbon. There are macro pores, which are the largest pores. These are basically the largest interstitial spaces inside the carbon. There are mesopores, MESO pores. Those are medium pores or mid pores, and then there are micropores, and those are the smallest pores. And the micropores are where the adsorption actually finally takes place and goes in. So if you look in the diagram there, you can see little specks and things going in and migrating their way down to the micropores. So the way that we like to look at it is the micropore is like a parking lot, and the mesopores are the highways that get you there, right? So it's all about balancing highways and parking spaces, right? So anybody that's been to an event, a concert, a game, anything like that knows that it takes the right mix of parking spaces and highways to get in and out to avoid congestion and backup. And that's why selecting the best carbon and matching the best carbon for your application is the right thing to do. So how does ion exchange work, and why does ion exchange work? Well, ion exchange is based on the principle of exchanging a harmless ion for the contaminant. So if you can see in the diagram on the right, the green contaminants then are exchanged with the yellow chloride ions, and the green contaminants are stuck on the ion exchange resin and are therefore exchanged for the chloride ions that go back. So it does take a small footprint because it does have a much smaller empty bed contact time, or a shorter empty bed contact time than granular activated carbon, typically in the range of 2 to 3 minutes versus 10 minutes or so for granular activated carbon. The life cycle costs are a little bit easier to predict because there's less interferences, and the spent carbon can be incinerated. For carbon, just kind of backing up a little bit, where carbon is really an omni-absorbent on organics, it will absorb other things in there. So other organics, naturally occurring, NOM, background TOC, other things that are in there. With ion exchange, it does compete with other ions, things like chloride, sulfates, other things that are naturally occurring in the water. So by looking at which one is the best fit really depends upon your influent water as well as your effluent guidelines and any other requirements in there. So it takes a very holistic approach, or it should take a very holistic approach to look at the front end to the back end. Shouldn't be a cookie cutter approach. It really should be a specific approach and a tailored approach, if you will, to solving the PFAS equation. So there are different ways we do this, and one of them, and the most primary way, is by performance testing. A pilot unit, which is shown in the diagram on the right, or bench scale testing, which you don't have a diagram of, but it's a small scale testing, is used to test the effectiveness of a technology for contaminant removal. And it's done before this community system is installed for drinking water or other types of applications, to basically help prove out the performance, to look at what you're going to be able to do for removals, as well as an expected life capacity. Accelerated bench scale testing, or an RSSCT, rapid small scale column testing, is another method that uses smaller columns that are about 2 centimeters in diameter, as opposed to the pilot scale, which you can see on the right, which uses column diameters from 2 to 4, maybe even 6 inches in diameter. The differences really between the two are the pilot scale, or the pilot test, is run on a slipstream of the influent contaminant. It takes a lot longer. Usually it's at anywhere from 6, 9 to 12 months to be able to run a full pilot versus an RSSCT, which can be run in a fraction of the time, typically 2 to 4, maybe 6 weeks, depending upon the longevity and the contaminants and all the other things in there. Pilot testing is usually recommended for surface waters or difficult waters. Excuse me. So, because you takes into account seasonality and other things. If you have groundwater that's pretty, I'll say pretty static, if you will, an RSSCT should give you a good picture of what you have, because the RSSCT uses a snapshot, a single grab sample, or even if you've done a composite over some time, but it's basically a one-time sample of the water that you're running through on a scale. And that's what we use to then basically scale up or provide information on throughputs, capacities, and performance of the system. So mobile units are also available. So there's different ways that these things can be mobilized, right? So on wheels or in skids or other things for rapid or emergency response, for temporary or semi-permanent installations. It's more than just drinking water applications. It's for construction dewatering. It could be for industrial processes or industrial wastewater in times of emergency or an event-based or an event-driven event. So if there's a down, like something happens with your wastewater treatment or heavy rains or something else that needs to be put in, there are opportunities to bring in mobile or temporary systems. The picture you see on your right is of a construction site in Michigan where they were doing construction and they were having to dewater, and they found PFAS and other contaminants in there, and we were able to mobilize equipment. This happened to be a combination of stuff that was on the ground and up on trailers that could be brought in and used to treat the water prior to discharge to the POTW. So it's like I said, the footprint can be variable, they can be skid mounted, and they can be tailored to specific site constraints. So now I'm going to cover a couple of case studies. So the first is water treatment at a construction site for contaminant removal. This also happens to be another site in Michigan where they were doing development in the West Michigan area, and they were under an edict because, of course, as you know, particularly in the north, there's certain times of construction before the ground freezes, so you have to be able to hit certain milestones to make sure you've got footings and diggings and other things done to be able to proceed with construction. In this case, there was a very high water table that required a lot of treatment, and there wasn't much room, so a tight footprint was needed. So in this case, there was PFAS at the site, which was higher than had been expected, so it was not able to be discharged back into the POTW. So we brought in some mobile units and some frac tanks and other things, as you can see in the picture, to store and contain and treat the construction dewatering and basically make sure that it was PFAS compliant for discharge. The treatment goal was met throughout the project, and the project was completed in, I believe, about 6 to 8 weeks' time. So in the same thing, this is another one, another construction site. And this is more of a downtown or an urban setting. The solutions were tapped directly off the wellhead, but they were trying to treat for not just PFAS, but arsenic, mercury, and other contaminants that were in the water that had to be treated prior to discharge. So again, units were brought in both as a combination on trailers and on the ground, and the water was treated and the cleaned effluent was discharged into a municipal sewer. Another one, which isn't a PFAS, but it just isn't a contaminant, maybe not an emerging contaminant, was an emergency solution installed to mitigate seasonal taste and odor issues at a site in Colorado, where they had MIB and jasmine in the water. The municipality had been looking to treat for this, but wasn't planning on designing, or was planning on designing a new facility, but wouldn't be able to get it implemented for a couple of years with permitting and construction and other things on there. But they needed a solution to treat for the seasonal water when tourists were coming in and others. So we did some RSSC testing to validate the offering, and it was a GA system, operated multiple vessels in parallel, and had a very successful treatment system that lasted for the summer and was taken offline in the fall. so that the vessels could be stored and they could put it back online for next summer. Another case study is at Kennebunk Port and Wells Water District in Maine. This is a very proactive community or a very proactive district. They tested many carbon systems and many carbon products. Evoqua was involved in the pilot testing to help support them, and we helped them determine which carbon, and they had decided that they wanted carbon, which was the best one to perform given their local water chemistry. In this case, the results showed that carbon made from coconut provided an additional 3 months of full-scale runtime versus other carbons. And I have in the following slide, it'll show you a little bit of the data that was used. In this case, they installed a full-scale high-pressure system to remove PFAS from water, and it was very successfully implemented and is still online today. As you can see here, as part of their pilot investigation, you can see the pilot unit that was actually on site on the right with the columns and the carbon in there. And you can see that they had about 10 nanograms or PPT of PFOA in the influent. They wanted to treat it down to non-detect. And you can see the curves and the performance from the bed lines of various carbons, standard 12 by 40 coconut, a standard 12 by 40 bituminous coal, and then our enhanced coconut, which is the CX. We piloted reactivated carbon, municipal reactivated carbon, as well as virgin carbon. In this case, the installed solution, you can see the picture up there in the top right. They had 3 vessels. The first one actually was a sand filter, and these are 12-foot diameter vessels. They injected a little bit of chlorine up front to precipitate the iron and remove it, and they backwashed it, and then they ran through a lead lag system of carbon using the AQUAVA 1230CX media. It was designed for a 10-minute empty bed contact time, but because of the seasonality of the system, it actually ran a little bit higher than that. So it ran a little lower, about an 8-minute empty bed contact time. It was originally an outdoor installation, which was then moved indoors. But they also have been doing custom segregated react and return. So they take that carbon back, reactivate it, and then it's made up, any of the attritional losses are made up with virgin carbon and put back in for reuse. So it's a very sustainable solution as well. One of the promotions on this is that if you can see the bottom right picture, is that they use these vessels that have a ring header, which is a septa design. So you can see the septas come up through the bottom of the tank. It allows for greater flexibility and allowing multi-use medias. So in other words, they could change these over from carbon to resin in the future if necessary. So it allows a lot of flexibility. It also means if anything happens on the internals, you don't have to enter the vessel to be able to do maintenance. You can drop the ring header and take care of repairs or other things in there without actually having to go inside the vessel. So basically, one of the great things about this is that it kept the community, it kept the utility independent without having to buy water or use water from another district. And basically, they didn't have any problems. The impact to the ratepayers was small, about 3 to 4 cents a day. And by the time everything gets pushed through, it'll be a couple of years before they actually see the rate increase. Here's another example of a case study. This was down in the Southeast United States. Pilot was also run on the feed water. You can see the pilot system there. The contaminants were PFOA and PFOS. It was a groundwater source that was influenced by firefighting foams. It was really an unknown source of where it came from. The concentrations were above the LHA, the Lifetime Health Advisory from the EPA. The water was very high in TOC, about 14 ppm, which is not unusual for Florida water. However, when we ran carbon initially, it fouled pretty quickly. So we switched it over to ion exchange resin, and the ion exchange resin, while it even turned black almost immediately, it continued to perform for great removal for a long period of time. So they ended up, instead of going with carbon, they ended up going with ion exchange resin. I said, so they ended up, their goal at the time was to treat to less than 10 ppt for all. So here are some of the results. You can see that after piloting, they ran at least 60,000 bed volumes before going out and seeing where they started to get breakthrough. There might have been a little bit of analytical error. You can see for the components there, for the hexane sulfonic acid and the octane sulfonic acid. They ran out through 150,000 bed volumes without breakthrough. And in the full-scale study, so they did a pilot and then they installed a full-scale. You can see that they got well over 100 million gallons of water processed through before they started seeing breakthrough in the vessels. So this was once again using resin as opposed to carbon. In this case, they did a full-scale comparison of resins from 4 different manufacturers. The vessels were spec'd with a septic design to provide greater flexibility. Some of the vessels did have a hybrid design, so there was carbon in some, and with also usually a carbon cap with a resin underbedding, or I should say resin as the primary, not an underbedding, but a carbon cap to help remove organics and maybe a little bit with taste and odor as well. But in this case, Evoqua's PSR2 plus resin turned out to be one of the better performing resins and was then used for rebeds in future versions. So I think we're now approaching the wrap-up session. So Jeff, I'll turn it back over to you. Thank you.
Thank you, John. That was really great, those case studies. So to wrap it up, we offer a portfolio of comprehensive solutions from start to finish. We can rapidly deploy mobile assets to your facility, offer treatability studies to help identify the best available technology today. I think we went over those with the pilots or the RSSCTs. Offer permanent on-site solutions. So after the fact that maybe we've done an initial setup, that we can install permanent on-site solutions. Employ a dynamic servicing network to your facilities, able to be on site in most of the US within 2 hours. And our reactivation services, which will help regenerate your carbon. And finally, our knowledge of disposal options to help you see it to the end. So what are the next steps? First thing is to assess risk, determine the regulatory requirements in your state, understand any public concerns and brand protection that you might have with the utility, obtain some background water quality and PFAS analysis. Can't stress that anymore. It's hard to set up and design systems without having some great analytical data, traditional water quality, as well as the PFAS analysis done on your water. Determine if there are any remedial alternatives. Understand the lifestyle costs of the system. Are there any destructive technologies that might be available? These things are these types of new technologies are coming all the time and right now in startup. And what are your disposal options? And finally, decide what type of upfront site-specific testing methodologies, whether it's a pilot or RSSCT, as John went over earlier. And lastly, just to summarize the whole program, is that your water is unique. So nobody's water is generally the same. So it's always good to provide the most information you can to your treatment technology company. So now we'll just pause for a minute and take time for questions. I don't know if any questions have come in.
Okay, well, excellent. Thank you both, John and Jeff, for your insights and expertise on the value of single source providers of emerging contaminant removal, including PFAS substances. We have a lot of questions. And I also wanted to remind the audience to please submit questions anytime now. We will get to them as we can. And if anything is unanswered during this webinar, we will have the folks get back with you after. So we'll start with our first question. And I'll just send this out to the two of you and you can jump in. Oh, actually, this one's for John. What is the minimum time required to do an adequate pilot test for an 800 GPM groundwater system?
Thank you, Billy. So I'd say based on, excuse me, for a groundwater system, we'd probably be looking at a rapid small scale column test or an RSSCT. If we were doing it with granular activated carbon, it would take about 6 weeks depending on concentrations. If it was decided to go with a pilot with carbon or resin, it would probably take closer to about a year. Like I said, it depending upon the concentrations, could be anywhere 9 months to 12 months, all depending upon what the treatment goals were and the concentrations in the water and any background organics or other, I'll say, any other ions that might be, you know, of concern in the water.
Okay, excellent. And we will direct our next question. Actually, this one's for Jeff. Jeff, let's see, do resin, pardon me. Apologies, gentlemen, I'm getting a bunch of questions all at once.
No
Jeff,
worries.
do resin and carbon
That's fine.
systems utilize the same type of pressure vessels? More specifically, can a GAC vessel be easily converted for use with resin?
A great question, Billy. A GAC vessel can be converted to an ion exchange resin vessel. So yes, on that one. The inlet distributor and the outlet screens must be selected appropriately based on the size of the resin.
Perfect, thank you, GAC. Great, I will know how to pronounce that now. Okay, question is for John. How do costs compare between carbon and resin?
Thank you, Billy. Resin is typically 3 to 5 times as expensive as GAC, but when considering the empty bed contact time for resin is 3 to 5 times less. Run times or run lengths, when you scale it out, while you may get significantly more bed volumes, you've got a fraction of the bed volume for resin that you do with carbon. So the typical run lengths, so throughputs as in gallons or days of runtime, tend to be pretty comparable. The PFAS composition, along with the influent, along with the overall treatment goals and whatever the bench or pilot scale testing determines, will actually help determine what is actually going to be the best CapEx and OpEx solution for a community or a user, whether it's a municipal or industrial user.
Okay, perfect. And we are getting lots of questions. So we'll just jump in again here. This question is from Melissa. Melissa wants to know, what are considerations for groundwater heavily impacted by road salt application, i.e. chloride?
I'll take that one,
John.
Billy, thank you. Yeah, I'll take that. So chloride is one of the ions that competes with anion exchange on the anion exchange resin. So heavy is kind of I guess a subjective term, but we would have to look at the chloride concentration. Usually if it's a few hundred ppm anion exchange resin, maybe okay. If it gets to be several hundred ppm, then there might be some interferences that we'd have to consider. And it's just not a matter of looking at one ion. You have to look at all the other ions in there, as well as what your PFAS contaminants are and their concentrations, whether they're short chain or long chain. Typically, resin does a little better job on the short chains, generally speaking in broad terms, than carbon does. Well, carbon is very effective as well. Sometimes resin does a little bit better on the short chains. So it all depends on what that actual heavy concentration is on the impact of salt, as well as what PFAS contaminants you have in your water and what your effluent guidelines, your treatment goals are. So good question, very good question.
Really understanding the water quality, right, John?
Correct. It's understanding the overall water quality and aligning that with your treatment goals, correct.
Okay, and this one is actually for Jeff. The question for Jeff is, what about in situ treatment options for PFAS?
Okay, thanks, Billy. For PFAS, the carbon fluorine bond is one of the strongest in chemistry, and that's what PFAS is comprised of. And the issue with in situ treatment methods, such as an oxidative process is that it would require a large amount of energy to break these bonds and ensure that, you know, all the compounds were completely destroyed and they wouldn't be forming any byproducts or other daughter products of PFAS. I think I mentioned earlier, there's all these, you know, there's over these precursors, and it's, you know, studies have shown over 5,000 compounds. So there's still a lot to learn there, but hopefully that answers it.
Okay, excellent. We'll jump to the next question. Does EVOQUA provide monitoring of the effluent to determine when breakthrough is occurring? And that would be for either one of you.
Sure, I'll take that one, Jeff.
Okay.
So this is John. So another good question. EVOQUA does not provide, well, we could provide monitoring, but usually it's not in the best interest. We don't do analytical. We're completely separate from that. We don't get into the analytical portion of it. So folks like Test America, Eurofins, SGS, any of the other labs that you may use, GEL, anybody that does that is separate. EVOQUA could do it under a service contract, but most of the time, if it's utility driven, so in other words, you're talking with the municipality, they have staff on payroll that can already do that as part of their routine sampling. So, but EVOQUA does not have its own laboratory for this, and to be honest, we want that impartiality in there as well. So, kind of making sure that the fox isn't guarding the hen house on the results, and a lot of times, particularly if it's a municipality, you want to make sure that you're using the lab that you're going to be having all of your state results run through for certification if it's testing. So I'm not sure if that actually answers the question or makes it worse, but so as far as on monitoring, EVOQUA doesn't do the actual analytical. We can help align you with labs, and if it's something that you're interested in a service contract for this, we can also provide that. But in most cases, if it's an industrial one where we're going out and doing things, yes. If it's a municipality, usually it's more economical for the user to do it unless they're, you know, a very small, a small utility and they don't have the staff to do it.
That is excellent. Thank you so much, John, for that. And thank you to the audience for all these fabulous questions you're sending. I have one for either of you to take. The question is from Stephen, and Stephen would like to know what kind of pre-treatment is required ahead of, is it IX, and what other type of substances compete for an active site in IX systems for PFAS? Is that how I pronounce that?
Yes, you did a good job. Okay. Thank you. I'll take that one, Billy. Thank you. Good, another good question. All good questions today. So for pre-treatment on IX, you want to remove things like iron and manganese, which will get in and foul the resin. You also want to remove chlorine. That's another thing we didn't cover earlier, but a very good question here, because ion exchange cannot have any oxidizers in there. So things like chlorine or oh my gosh, I'm drawing a blank, but I wonder what's the other, chloramines, excuse me, have to be removed prior to running through the ion exchange resin. We also recommend particle filtration prior to IX, because IX really can't be backwashed, at least not like carbon once it goes online, because you don't want to fluidize and disturb the bed. So we recommend usually a robust filtration, like as in bag filters or other type of particulate, 5 micron or less, to remove anything ahead of the system, as well as pre-treatment to remove any, excuse me, any iron or manganese or other potentially fouling or scaling components. As far as interferences, like I said, chloride's one of the interferences, sulfate, other anions that may compete, but you know, other things that may come up might be perchlorate, but if you've got that in your water, you've got to remove it anyway. So the ion exchange resin for PFAS will actually remove perchlorate and some other treatment and contaminants in there. So you may get kind of a 2-for-1 with that. But as far as on pre-treatment, like I said, you want to make sure that you remove iron, manganese, other maybe metals up front that may be in there that may present problems, either precipitating in the bed or accumulating in the bed, either in dissolved to precipitated form. So if it's dissolved, it comes through and precipitates in the bed, or actually building up on top of the bed.
Excellent. And just a quick follow-up on that. Does EVOQUA do GAC or IX changeouts?
Yes, EVOQUA does both. Yeah, we provide turnkey service on both.
Excellent, thank you. And let's see, trying to find a question where you haven't already answered. Joseph would like to know, was any speciation needed of the various PFAS varieties in case different PFAS species had different absorption and exchange characteristics?
I'm not sure what.
So I don't know if you're talking about like chromatographic separation up front or looking at, I guess maybe I'm a little unsure of the question myself, but we do know that the carboxylic acids, so the PFAS compounds that end in the A versus the ones that end in the S, so the sulfonics, typically the sulfonics are better absorbed than the carboxylic acid, so the carboxylics will tend to break through a little earlier. The shorter chain, particularly the shorter chain carboxylics, will break through before the shorter chain sulfonic acids. So you kind of have to know that going in so that you can basically plan or predict your breakthroughs and looking at what your balance will be. You know, some people are talking about doing a combination carbon and resin system. It hasn't really, there are certain applications where it does work and certain applications where it may not make sense. People have looked at both. We have some applications where we're doing carbon and resin in the same, not mixed together, but layered, like we were talking about the system in Florida, where they have a hybrid bed, if you will, of carbon and resin. So I don't know if that specifically answers your question, but if not, you can hit us up later. You've got our emails down there on the screen now. So my apologies if I didn't, but I hope that answered at least most of it.
And that's perfect. I think also for a slight clarification, maybe what would you suggest between rapid test versus a full-scale pilot?
Sure. So for me, it would, you know, we'd have to look at the chemistry of the water, right? The overall concentrations. And so basically what's in it for cations and anions, as well as what contaminants are in there. If it's a surface water or a water source that is partial to changing or I'll say influenced by other sources, if it's a river water or surface water, it's got something flowing into it. You know, even if it's something industrial, a parking lot, you know, that's treating runoff from a parking lot, so heavy rains or other things that may contribute to that. If you're looking at that, typically we would recommend something along the lines of a pilot, where it would be more long-term predictive to cover the seasonality of the fluctuations of the influent water. If it's a pretty static water source, like a groundwater that's pretty stable, that's not maybe under the influence of a surface water, then a rapid small-scale column test usually provides a pretty accurate depiction of what you're going to get in a full scale.
Perfect, thank you. And we'll go ahead and switch over to a question for Jeff. Little different line, but Jeff, what is the typical process for these projects from discovery to installation?
Oh, thanks, Bill. Another good question. So after you've confirmed detections of PFAS by a utility, that's usually the first, or industrial, it would start with engagement of either the general contractor, engineer, whether it's in-house or external, just to kind of come up with what's the situational analysis, what's going on at the site. In many cases, we've seen speed is an important consideration when choosing a solution. So timing, we always ask, you know, what's the timing of this? What's the, you know, how quick do you need this done? And then that can then set up some of the, whether you do an RSSAT or additional or a complete pilot. But the solution usually depends on each customer's specific needs, because as I mentioned earlier, each site is different. Your water is unique. We recommend, you know, pilot and or bench scale performance tests prior to do anything. And these tests, along with the you know, our customers' criteria of budget, the timing again, what the treatment goals might be, that'll help determine what's the best system and what's the correct media to use.
Excellent, thank you so much. Okay, I'm gonna put this out to you and Jeff and John. Does EVOQUA have NSF 60-61 certified materials and vessels in parentheses, only used for potable water for emergency drinking water treatment?
I'll handle that one.
Yeah.
Thank you. Great question. Yes, we do. We have dedicated fleets of equipment and tankers that are potable only. So they only are used in potable applications. So it's a completely separate fleet. We also, for granular activated carbon, we also have a dedicated plant, reactivation plant in Darlington, Pennsylvania, which is able to process NSF 61. So for municipal and other potable applications, food and beverage, other things along those lines, that can be NSF certified for custom segregated react. So we could take your carbon for a municipality or beverage, reactivate it and give it back to you with makeup, virgin makeup. All of our medias that we would use in these applications are NSF 61 certified. And like I said, our components, the components of our vessels, all of the wetted materials, all the other things are NSF 61 compliant.
Oh, great. Thank you. Great answer there. Okay, we'll head to a question from Atosa. Atosa would like to know, what is the effect of TOC and nitrate on absorption? Let me try that again. What is the effect of TOC and nitrate on absorption model? Apologies, gentlemen.
Yeah, no worries. This is John. I'll take that one. Thank you. Another great question. So TOC, particularly on granular activated carbon, is going to consume more of the carbon. So most TOC has a higher affinity for absorption, or the carbon has a higher affinity for absorption or stronger absorption rate of TOC than it does for PFAS. PFAS, while it's got some hydrophobic and hydrophilic properties that make it, great for stain and water resistance, but it also makes it a little bit harder to attract and absorb. So high TOC waters would probably have a tendency to skew more towards ion exchange resin. Nitrate is another interference on the resin that will get absorbed. So if you have water with high nitrates, then ion exchange resin may or may not be a fit. Once again, it'll depend on profiling your water. So taking a look at once again, going back to a more holistic approach, looking at your water chemistry from a cation and an anion, which would include, and then we'd kind of lump TOC in there. We have like a standard discovery form that says, these are the things we need to look at to provide a general evaluation, and then sampling and other things. So for higher TOC waters, resin is typically more effective. For higher anion content waters, then usually carbon might be a better offer. But that's, like I said, that's just kind of a rule of thumb. It's not a strict guideline. It depends, once again, on what your treatment goals are and what else is in your water, right? Because there could be certain things that if you're, while you may have a higher TOC, you may not have the ability or the desire to dechlorinate your water prior. So in that case, carbon may be a better option. For other things on anions, if it's too high in interfering anions, then carbon may be a better option again. So it all depends on what your treatment goals are and what your influent water is, as well as what other requirements. It's budget, it's footprint, it's operators. I know, just as in general, at least I'm in Massachusetts, in my neck of the woods, so to speak. Operation from a municipality or from a utility, a municipal water treatment, carbon and resin are different grades of operators, right? So I think it's a grade 2 for a carbon system and a grade 3 or a level 2, level 3 to operate. So if you're going with a carbon system and you have grade 2 operators, you're fine. If you're going with a resin system and all of your operators are 2, you're going to have to get in 3 or train your level 2 operators up to a 3. So it's something that the municipality has to take in as an operational consideration, as well as part of the overall system approach.
Okay, great. Thank you. I know you were talking about Massachusetts. How about we move to Florida? For the Florida high TOC GW, what is the resin treated water level of TOC?
I believe it was about 14 ppm. I thought that was on one of the slides, but it was about 14 ppm of TOC in the influent. And like I said, maybe I went through it a little too quickly, so my apologies on that. So when we piloted, originally started looking at carbon, the carbon in essence plugged after about 3 days of operation. The pressure drop was so high, we just stopped. We rebedded the pilot, we cleaned it, rebedded it with ion exchange resin, The resin turned black within 24 hours. All the resins, all 4 resins turned black within 24 hours, but there was no pressure drop and performance continued and the pilot ran for months.
Excellent. Thank you so much for that.
You're welcome.
Let's move over to Jeff for a question. Jeff, if the carbon is less expensive than resin, is there any application scheme with a series of carbon followed by resin?
Can you repeat that again, Billy?
Absolutely. If carbon is less expensive than resin, is there any application scheme with a series of carbon followed by resin?
Yeah, I think as John mentioned, you can have a system where you have combination of both carbon and resin.
Yeah, correct. There are instances where some people want to look. So carbon is less expensive, but you have to use 5 times as much. That's going back to what I had said about the comparison between the two. So, you know, while you have 10 minutes of empty bed contact time versus 2 to 3, and the expense of the carbon, I'll say the costs, other than the vessel costs, using smaller vessels for ion exchange helps reduce the CapEx investment up front. From an ongoing exchange perspective or looking at volumes, then I won't say it's a wash because there's other considerations in there about disposal and return and other things are in there. But to answer the question, carbon can be used as an effective, if you will, pre-treatment ahead of resin, or using resin as a polisher to maybe clean up some short chains or breakthrough on the very end. So that is a viable application or a viable opportunity, let's put it that way. It can be done.
Oh, great. Excellent. Thank you. And next question is, does Evoqua provide temporary systems for treatment of concentrated AFFF PFAS waste streams from firefighting incidents?
I'll take that one.
Yep.
Thank you, Billy. Another good question. Yes, we have done some temporary applications with I'll say airports and other institutions, I'll leave it at that, where they've been having to treat from either a spray down in a hangar that's collected into a sump, or other things where we've had to treat kind of higher concentrations as opposed to drinking water, which typically drinking water is in the PPT, PP low, maybe low PPB if it's severe, whereas you're talking about PPM concentrations. Obviously, the run times are much shorter, but carbon or resin can be effectively used in either application for treating AFFF solutions as a result of spills or cleanups at airports, military bases, other industrial sites. And we do have temporary systems that can be used to mobilize that. Once again, going back, I know there was a previous question, separate from our potable and drinking water asset and fleets.
Perfect. Thank you. Next question, and we'll take a couple more questions and then wrap it up. How many membrane removal systems have you done for PFAS/PFOA removal?
I'll take that one.
Take that, John.
Evoqua, yeah, thank you. Another good question. Evoqua has not installed any membrane systems for PFAS removal. We know of 2 that have been installed by others throughout the country. I think one is in North Carolina, the other is in, I believe, Alabama. I know in the case of North Carolina, it was done over other I'll say capture the capture technologies versus the separation, because there was just so much in the water. It was a veritable witch's brew, if you will, of contaminants. It didn't have just PFAS in it. It had dioxane. It had, I believe it had some pesticides. It had other things in there. So as opposed to having a multiple flow sheet designed for removal of every single component separately, they just decided to put in a membrane system to treat the water and then deal with the concentrate separately. But Evoqua has not used any membrane systems commercially for either municipal or other, where we've put in an RO or an NF system specifically treating for PFAS to concentrate and reject. But it is an available technology. It is offered. We just haven't put any in.
Okay, perfect. quick question we have here for you is, are you finding a preference of GAC or resin for short chain PFCs versus the long chain PFCs?
This is John, I'll handle that one. So thank you, another good question. So most people, and one of the questions we've had, that has come up before is, typically ion exchange resins work a little more effectively. Not that carbon doesn't work effectively, it just usually doesn't last as long. But once again, if you're just looking at short chains, ion exchange might be a better option because they are a little bit better at removal of short chains than carbon. But once again, if it's just a short chain stream, then that might be it. But it's a case-by-case basis. Once again, looking at your influent, the characteristics of your influent, and then looking at what your effluent guidelines are, so what you're going to be treating to and discharging, really will tell you what the right solution is.
Okay, great. And just one last question. The person asking the question said they understand water chemistry and permitting is specific, but would like to know, does AQUAVA recommend CMF for precipitated solids removal to extend GAC lifespan?
So this is John Lombardo, I'll take that again. So I believe the CMF is cross-flow microfiltration. To remove solids up front, if it's a high enough suspended solids application, absolutely. Once again, you really don't want to disturb these beds, particularly in PFAS. I know for granular activated carbon, for I'll say the more traditional long-term applications, if you're doing it for chlorine or chloramine removal, as well as maybe MIB or Jasmine removal or some of the other ones, backwashing might not be as big a concern. For PFAS, it is a concern. We try to minimize backwash at all costs, whether it's an ion exchange or a carbon system, just because you don't want to turn over the bed, and because PFAS is so weakly ionized, if you will, so it's on the lower end of the selection spectrum. So you don't want to turn that bed over and give a chance to kind of I'll say have a reverse chromatographic effect happen, where you're kind of rolling off some of the PFAS into the effluent where it's being displaced by longer chains. So some of the shorter, the longer, or higher concentration, lower concentrations. So bed rollover is a concern. So we just want to make sure that you're trying not to disturb the bed once it's been put in place. If the solid content is high enough, it's an industrial application that has things where you're trying to precipitate things out, either using some type of either ferrous sulfate or aluminum chloride, or some other type of coagulant, and then flocculant to do that, and then you're going to use a CMF to remove it. That would be a great thing, but that would be more, I think, we haven't seen any of that on the municipal side. On the industrial side, that would probably be a very likely scenario if it was like a wastewater application.
Okay, gentlemen, anything else you'd like to add before we conclude the webinar?
No, just we thank everyone for their time and attendance and for the great questions. That was a really great Q&A, at least from our perspective. If you asked a question and we didn't answer it, or you need it further, just let us know and we will try and get back to everybody.
Yeah, thanks again, everybody, for joining today.
Thank you. And thank you again, Jeff and John, for your insights and expertise today. That does conclude our webinar on the value of single source providers of emerging contaminant removal, including PFAS substances. Before we go, I hope you will join us at one of our upcoming webinars. You can learn more at awwa.org/webinars. And please don't forget to participate in the survey immediately following the webinar. Until next time, thank you for keeping the water safe and secure, and have a wonderful day.